Okay, well, welcome back to Math 140, everybody. Um, I wanted to use this first little video to try to get us sort of back in the swing of things, and maybe the best way to do that would be to think about the homework that we sort of left off at the end of um, the last week of classes. There, I did give an assignment that I was gonna make due the Monday we got back, but now obviously I've extended that. So there is an assignment that's due Monday, the 23rd of March, which is our first day back. It's this homework 28 on the second derivative test, and it also has to do with concavity and things like that. And I did go ahead and make it due at 11 o'clock in the evening. After thinking about it again, making it due at 10:30 didn't make much sense since we're not meeting at 10:30 in the morning anymore. So homework 28 is due at 11, and if we just sort of pop it open, you can see a little bit of what's in store here. Um, so it's basically talking about the information that the second derivative of a function can give us about that function. So this has to do with the concepts of concavity and inflection points and the second derivative test for a relative maximum or a minimum. So I thought I'd take just a few minutes here and recap those concepts for you and maybe work through an example in which we're doing similar kind of things to what you're going to be doing in homework 28. So let me see if I can make all this work. I wanted to first just uh, sort of go over kind of conceptually what the information in the second derivative is telling us about a function. So I've just got a kind of a generic function here. It's the purple curve, the kind of sine wave looking curve you see there. And on top of it, I've sketched little tangent lines at various points along the graph. And the way to start beginning to think about the second derivative is to think about what's happening to the slopes of these tangent lines as you move from left to right along the graph. So as x increases, and I've kind of if you think about it here, like starting here at the left corner, the slope of the tangent line at this value of x, whatever that would be, is pretty large, and it's a positive slope, right? The line is rising from left to right. Now think about what happens to those slopes as you as you progress, as x starts increasing, as you move from left to right. Large positive slope, like maybe 5 here, but as we move to the right, the slopes start decreasing, right? So this slope here is not as steep as it was back here. So the slope is decreasing of those tangent lines until when you get to the very peak of the graph, which would be somewhere around here, you've actually got a tangent line. So if that's the peak, you've actually got a tangent line whose slope is 0 there. And that relates back to the first derivative that we had talked about in the week before we broke for spring break. So what you see then is that the slopes of these tangent lines are decreasing. They start out large and positive, and they get down to 0. And actually, as you keep moving, the slopes continue to decrease. The slope becomes negative once you move past the peak. So if the slope is decreasing, of course, slope means derivative. So that says that f prime is decreasing. Now, that doesn't last forever for this graph, though. The slopes keep decreasing, but at some point, and I've kind of just eyeballed it here at this point on the graph, at some point that trend stops, because if you start looking to the right of this vertical line here, you see that the slopes actually start increasing again, right? Like right here, The slope is at its most negative that it gets. And then as you keep moving, the slopes start increasing until when you get down to the valley here in the graph, right there at the trough, you've got again a slope of 0. Of course, that's a critical point, and we talked about that in relation to the first derivative test. But what I want to just point out now is that after this point, the slopes start increasing again, and of course that means that f prime is increasing, because f prime is the slope of the tangent line. So now if you relate this back to some of the ideas we talked about when we were talking about increasing and decreasing functions, what does it mean when we say a function is decreasing? Well, we saw earlier that meant its derivative is negative. So if we're saying over here in this left part of the picture that f prime is decreasing, what that corresponds to is the fact that the derivative of f prime, which would be f double prime, it would be less than 0. If a function is decreasing, its derivative is negative. And so if our function f prime is decreasing, that means that its derivative, which would be f double prime, is negative. And similarly over here, if we're saying that f prime is increasing, what does that say about the derivative of f prime? It would say that the derivative of f prime, which again is f double prime, would be bigger than 0, would be positive. Now these things have to do with the shape of the graph. When f prime is decreasing like it is here on the left, we say the shape is concave down. Whereas if f prime is increasing like it is here on the right, we say the shape is concave up. Sometimes people remember that concave up holds water, concave down doesn't. But that's the basic idea. And so the second derivative, because it just matters as to whether the second derivative is negative or positive here, gives us information about that shape, concave up or concave down. So the basic idea would be that f is concave down, like it is here on the left, just in case the second derivative is negative. And f is concave up if the second derivative is positive. And so that's a really nice way of seeing whether a function kind of has that concave up or concave down shape by just looking at the second derivative. But there's a little more to it than that as well, because the second derivative can tell us about peaks and valleys of a function. These points here where the first derivative is 0. Think about it for a second. What if I told you that I've got a point, let's call it C. I'm going to call out this point right here, that x value C, where the derivative is 0. What if I told you that f prime of C is equal to 0 and f double prime of C is less than 0? What could you make of that? Well, think about it. F double prime of C less than 0, that says we're concave down. So we have this kind of shape. And f prime of C equals 0 says we've got a flat tangent line. So if you combine those two things, you've got a flat tangent line and you're concave down, you see that you have to be at a peak. And so that would say that the point C comma f of C is a relative maximum value for f. And similarly, if you think about the other kind of situation where you've got a place where you've got a flat tangent line, so f prime of C equals 0. So I'm now thinking about this place over here. And I told you that, look, hey, the second derivative at that point is actually bigger than 0. Then what could you make of that? Well, you would know two things. First of all, since the second derivative is bigger than 0, you're concave up, so you have that holds water kind of shape. But then since the first derivative at c is equal to 0, you got a flat tangent line. Putting those two things together tells you that you've got to be at a minimum, at a valley in the graph. So c comma f of c is a relative minimum for f. And those two ideas together are called the second derivative test. And so it's a really good way of determining whether a function with a whether a critical point is a max or a min. You look at the second derivative and think about concavity, and you'll come up with the right answer. Now there's one caveat here. We've talked about when f double prime is negative and f double prime is positive. What if f double prime is exactly equal to 0? Well, in that case, the second derivative test just doesn't tell us anything. It may be a max, it may be a min. The bottom line is if f prime of c equals 0 and f double prime of c equals 0, then the second derivative test simply draws no conclusion at all. In other words, in that case, you may have a max, you may have a min, you may have neither. You just don't know. You have to do something else. And as we discussed in class, the thing you do in that case is go back to the first derivative test. So the second derivative test is typically quicker and easier to do than the first derivative test, but it does have this kind of caveat that sometimes it just doesn't allow us to draw a conclusion. And in that case, you go back to the first derivative test. There's one other thing I wanted to point out about this situation here, and let me get another color. A point like this, this point that sort of demarcated the dividing line between concave up and concave down, that point on the graph, if this is, I don't know, let's call this value x equal d, that point where the concavity changes, so it would be d comma f of d, that's called an inflection point for the graph. It's an inflection point is a place where the concavity changes, and so that's that. It's kind of hard to eyeball just on the graph. It's harder to eyeball than a peak or a valley, but you can do it. But we'll see in this example that I'm about to do that it's easy to spot inflection points once you just look at the second derivative. So let's take an example now, and I've got a fairly simple one here set up where we're going to find, we've got a function f, it's x to the fourth minus x cubed. I hope you can read that, and we want to find the intervals where f is concave up and concave down, and also the inflection points of f. And we'll also go ahead and look at the second derivative test and see if we can classify the critical points. So the way to get started on a problem like this is, of course, to compute derivatives. I've gone ahead and computed the first derivative here of our function f, and it's pretty easy. And I went ahead and factored it. The reason I factored it is because that helps us to find critical points, which we'll need later when we apply the second derivative test. Critical points, are places where the first derivative is either 0 or undefined. Now, if you're in this case, the derivative is a polynomial, it's always defined, but we can go ahead and find critical points since the thing is factored. And factoring is easy, right? We just took out the common term x squared and pulled that out, and we got x squared times 4x minus 3. So the critical points are places where the derivative is 0 or undefined. In this case, it'd just be 0. The only way this can be 0 is either x is 0 or 4x minus 3 is 0. That would mean that 4x equals 3 or x would equal 3/4. So those are critical points, and we'll just put those in our back pocket until we need them a little later. To find intervals where f is either concave up or concave down, what you need to do is find places where the second derivative is positive or negative. So let's go ahead and compute the second derivative of this guy, f double prime of x. Actually, in computing the second derivative, it's a lot easier to use the unfactored form because you don't have to use the product rule in this case. So that would be 12x squared minus 6x. And the way to determine concavity is to build a sign chart for f double prime, because that'll tell you where f double prime is positive, which means concave up, or negative, which means concave down. So we're going to build a sign chart, SIGN, for f double prime. And to build that sign chart, it is, again, helpful to have the second derivative factored. So now I'll go ahead and factor it. In this case, I can pull out a 6x. That's a common factor. And I'm left with 2x minus 1. And so to build the sign chart for f double prime, it's a lot like building the sign chart for f prime. You first find the place where the second derivative is 0. So looking at that, the second derivative, and that's where the factored form helps, the second derivative can be 0 if either x is 0, so I'll put that there, or 2x minus 1 is 0. And that would mean 2x is 1, so x would be a half. So I'll put that over here. And both of those places are places where the second derivative is 0. And once you've got those, you can just use test points in each interval to figure out what the sign of the second derivative is. So like for this left-hand interval here to the left of 0, use a test point of -1. If x is -1, I'd have negative times negative, and so that's going to be positive. For x between 0 and a half, I could use a test point of a fourth, right? 6 times a fourth is a positive number. 2 times a fourth is a half, and a half minus 1 is negative. So I'd have a negative times a positive, so that would give me a negative. So my second derivative is negative in that region between 0 and a half. And for this last interval, I could take a test point of x equal 1. So I get 6 times 1, which is positive, and then 2 times 1 minus 1, or that's positive. So positive times positive just gives me positive. And so that tells me that the sign of the second derivative. So then relating that to concavity, I would know that f is concave up on the intervals where the second derivative is positive. So that would be minus infinity to 0 and 1/2 to infinity. And then f is concave down on the intervals where the second derivative is negative, and so that's going to be 0 to 1/2. And so there we know that, and you know, that tells us something about the shape of the graph there. So that's the information the second derivative gives us about concavity. But we can also use the second derivative test to classify critical points. And so if we do that, let's go back up here now to our critical points, x equals 0 and x equal 3/4. And let's see, in order to classify these, I want to examine what the concavity of these two points looks like. So let me just kind of mark off a little area over here where I can do this. So we'll do the second derivative test to classify our critical points. Let me start with x equal 3/4. So the critical point, x equal 3/4, we know it's a place where it has a flat tangent line. So the question is, well, if I knew what the concavity was, then I would be able to determine if it's a max or a min. So let's look at its concavity. You could just compute f double prime of 3/4. And here again, I've got f double prime right here. I'm going to use the factored form because it's a little easier here. 6 times 3/4 and then times 2 times 3/4 minus 1. What you see is that you could work this out, of course, but the point would be that this is going to be a positive number because 6 times 3/4 is positive, and then 2 times 3/4 is bigger than 1, right? And then you subtract 1 from that, it's still positive. So this number is positive. So what it says then is that at 3/4 we got a flat tangent line and we're concave up, right? So imagine that. Flat tangent line, concave up. That means that x equal 3/4 has to be a relative min. So x equals 3/4 provides a relative min. In WebAssign, they'll want you to give the y value too, and the y value, remember, you're going to plug this x value all the way back into f. WebAssign would ask for the relative min in the form x comma y be 3/4 comma, and then you'd plug that 3/4 back into f to get that point. And I think I may have done that already. Let's see if I can find my notes here. Yeah, f of 3/4 turns out to be minus, so 3/4 is 0.75, and f of 3/4 turned out to be minus 0.0547, and I rounded that last digit. So that would be the relative minimum point on our graph. And then let me continue down here. The second derivative test for the critical point x equals 0. Here's where the second derivative gives us a problem, right? Because f double prime of 0, I'm plugging x equals 0 in here. That's going to give me a big fat 0. And so there's no conclusion from the second derivative test. Now, I won't do this right here, but if you go back and do the first derivative test for x equals 0, you'll find that the first derivative doesn't actually change sign. And so it turns out that the x equals 0 is neither a max or a min. So the first derivative test shows that x equals 0 is neither a max or a min. And then finally, what about inflection points? Well, inflection points, again, are places where the concavity changes. And so the inflection points are going to occur at x equals 0, this guy, and x equal 1/2. And again, WebAssign, so this will be an inflection point here. It'll be 0 comma f of 0. Again, you plug the x value where the concavity changes back into f to get the y value, and this is the way WebAssign usually will ask for the your response. 0 comma f of 0. If you plug in 0 back here to f, you see that you get 0. So one inflection point for this graph is 0, 0. The other inflection point is this guy right here. So that's another point of inflection. And the actual inflection point would be x equal a half, y equal f of 1/2. So you're plugging again back into f. So this would be 1/2. And f of 1/2 turns out to be minus 0.0625. I just used my calculator for that. So that would be the other inflection point. So yeah, there you have it. The second derivative can give us valuable information not only about the shape, the concavity of a function, but also about whether critical points are relative maxes and mins. So I hope this helps you as you work with homework 28. I'll be back in touch again soon with some more videos, and we'll begin to make some more progress as we learn how to apply these calculus concepts to some problems in economics. So until then, be well, stay safe, and again, if you have any questions, please email me at my Hamden Sydney email address. And one note, I will be setting up some virtual conferences so we can do some chats and have office hours. But again, I'm still working on that, so bear with me as I get used to doing things in this new sort of online way. In the meantime, take care, and I'll be back in touch soon. Bye now.